that leads us to the next point, which is, let's say that you have this data you collected with the same mean, 50, and the same standard deviation, 10. But now, let's say that you plot it to make sure that you can use this bell curve relationship. But when you plot it now, let's say it looks like this. And it happens to not look like a bell curve. So the question is whether you can reach the same conclusion. So previously, when you had this distribution, when the mean was here, you were able to say that all these values that lied around the mean of 50, you're able to say that that constituted 95%. So if you looked at all these values here, then that constituted 95% of the values, where these values left out, that only represented 5%. And so that made sense for this bell curve relationship. But what if you had plotted the histogram for this variable, and it no longer looks like a bell curve, but it looks like this, where this is the mean here at 50? Do you think all these values between 30 and 70, let's say 30 and 70 are down here, do you think in this case, this will constitute 95% of the population? Yeah, you notice that because you have a lot of values now at the extremes that are left out, that are bigger than 70 and less than 30, so you would imagine that this percentage will be a lot less than the 95% if the distribution looked different. And so now, we want to basically answer the same question, but what if you had plotted it and it no longer looks like a bell curve? What would the answer to the question be? And so, it turns out that we have a relationship that addresses this for any distribution and not just bell curves anymore. And this is something called Chebyshev's theorem. So Chebyshev's theorem answers this very question for any distribution and not just bell curves. So Chebyshev was a Russian mathematician, not to be confused with Chebyshev. Tough crowd. So Chebyshev's theorem answers this very question of the percentage of the population that has values in a certain range. So I'll go ahead and write that out. The percentage of the population within a certain number of standard deviations from the mean, which we'll call K, within K standard deviations. Of the mean. Is going to be at least one minus 1 over K squared. Okay, so right now that probably looks very complicated, but let's apply it onto this example. So again, this example has the same numbers as before. The mean is 50, the standard deviation is 10. So we want to answer this question, is what percentage of all values is between 30 and 70? But we can no longer use the bell curve relationship we just talked about, so we're going to use this relationship that applies to all distributions. And this says that these values being k standard deviations from the mean. So first of all, these boundary points between 30 and 70 represent values within how many standard deviations of the mean. So same as before, it's still 2. Again, going from the mean of 50 to any of these boundary points, you're going 20 units, and each standard deviation has 10 units. So therefore, those 20 units translate to 2 standard deviations in each direction. So all these values between 30 and 70 are within 2 standard deviations of the mean. So the value of k here in this example will be 2. So all you would have to do is plug in 2 in here. So if you plug in 2, you're going to get 1 over 2 squared, which is 1 over 4. And you're going to get 1 minus 1 over 4, which ends up being 3/4, which is 75%. So the answer to this question will be, so one important point is not only the number of 75%, but the other important point is this word at least. So the word at least acknowledges that you don't know the definitive answer, because this distribution can be anything, not necessarily just a bell curve. So this theorem applies to all distributions. And so we're saying that this answer represents a lower bound. Whatever the true answer is, it can't be less than this number of 75% that we calculated. It could be equal to or more. So it could be possibly any number equal to or greater than this number of 75%. Any questions? And so because this theorem applies to all distributions, the final answer can't be definitive. That's why there's this lower bound. Okay. Any questions? So let's say that in this example, later on you go and plot this distribution. So let's say that the first time around, you didn't plot the distribution. So because you didn't plot the distribution, you don't know whether it's a bell curve or not. So you can't specifically use the bell curve relationship to make your conclusion. So therefore you use this Chebyshev's theorem that applies to all distributions, bell curves as well as not bell curves. You reach this answer that the percentage of values between 30 and 70 has to be at least 75%. So that's your answer for now. But then later, let's say, much later on, then you decide that you have the time and energy to actually plot the distribution, and you see it's a bell curve. And because you see specifically it's a bell curve, that the answer will be exactly 95%. So these two answers that you got, one is at least 75%, and one is equal to 95%. So are those contradictory to each other? Are those answers consistent or not? Yeah.
They're not technically contradictory with the at least boundary, but they're definitely not very descriptive of the data.
Yeah. So the more you know about the distribution, the more of an exact answer you can give. Which is, if you know that this is specifically a bell curve, then you can give a more exact answer of 95%. But if you don't know much about the distribution, then you can at least give an ambiguous answer. An ambiguous answer is that it's at least 75%. It can't be less than 75%. So the answers are not contradictory to each other, they're actually supporting each other, but one is more specific, depending on the fact that you know the specificity of the actual distribution. Yeah.
So we can always get the standard deviation, but we can't always get the percentage.
Short answer is yes. Because based on the data set you collect, you can always punch those numbers in your calculator to get the mean and standard deviation for those numbers that you just observed. But if you have the actual numbers in front of you, if you had all the population numbers, then yeah, you could get the percentage, but usually you don't have all the population numbers. You only have the sample numbers. So the point is that just by these two summary numbers, you can make a conclusion about these percentages. Okay, any questions? All right. Let's do another quick practice. So let's say that we have a test, let's say, and the professor announces what the mean and standard deviation for that test is. So let's say that the mean is 60 and the standard deviation is 5. Let's say that we know that this relationship we talked about only applies to bell curves, but let's say that you don't bother plotting the curve yet, so you don't know whether it's a bell curve or not. So, based on the limited information you have, what percentage of all data, of all test scores, are between let's say 55 and 65. In other words, what percentage of all test scores are within one standard deviation of the mean? 68. Okay, so this 68 applies specifically to a bell curve relationship. So if you know that these grades are distributed in a bell curve, then yes, you can make this determination. But for now, let's say that you don't bother plotting the distribution, so you don't know specifically whether it's a bell curve yet.
At least 0%?
Yeah, so what you would have to do is, you would have to use Chebyshev's theorem, but you notice Chebyshev's theorem, you would have to plug in k, and so k represents the number of standard deviations that these values are within the mean. So, yeah, how many standard deviations? So if you go from 60 to each of these boundary points, then how many standard deviations are you going? Yeah, one standard deviation. So so k in this example is going to be 1. So if you try to plug in k into here, then what do you get? 1 minus 1 over 1 squared,
0.
which is 0. So yes, Chebyshev's theorem here is giving you an answer, but is it a very useful answer?
No.
No, it's not useful because it's saying that the answer is at least 0%. Well, I mean, that's obvious, right? So we could have said that without using any formula. So the first thing I want you to get from this is that Chebyshev's theorem only gives you a useful answer if k is above 1 standard deviation. In this case, k was only 1, so we're not getting a very useful answer. So what if this had been changed to all test scores within 2 standard deviations, i.e. between, so within 1 standard deviation, we're looking at values between 55 to 65, and we said that Chebyshev's theorem was giving us an answer of 0%, which is not very useful. So what about within 2 standard deviations?
75%.
Yeah, so within 2 standard deviations would be between 50 to 70. So what percentage would that be? Yeah, so if you plug in 2 here, you're gonna get 1 over 2 squared, which is 1 over 4, and 1 minus 1 over 4 will be 75%. And you're gonna have this lower bound, so the answer will be at least 75%. So that's a little bit more informative, but you still have ambiguity in there, because you don't know whether the true answer is exactly 75% or whether it's any number between 75 and 100. Okay, any questions so far? Okay, so then, let's say later on you decide to plot the actual distribution for these test scores. And you see that now, it's an actual bell curve. So then the answer to the same question of all values within 2 standard deviations of the mean, or between 50 and 70 in this case, would constitute what percentage of all the test scores?
95.
Yeah, so now that you know it's a bell curve and you plug in 2 standard deviations, you'll see that the answer will be 95% of all test scores are within these values. So this will be 95% of all the test scores will be between 50 and 70. So the point is that the number of standard deviations from the mean will give you an idea of how extreme the values are. So the more number of standard deviations you go out from the mean, the more extreme the values will be, and the closer the values are from the mean in terms of the number of standard deviations, the more typical the values will be. Yeah.
In a bell curve, would 4 standard deviations be considered 100%?
Yeah, so it turns out that you can never be exactly at 100%, but the more standard deviations you go out, then the closer you will be to 100%. So right now, at 3 standard deviations, we're at 99.7%, and it turns out that for 4 standard deviations, again, you don't have to memorize these numbers. What I want you to get from this is that for bell curves, there's a definite relationship between the percentage of the population and the number of standard deviations from the mean. So for 4 standard deviations, it turns out to be 99.99%, so almost 100%. Any questions? All right. So it turns out that this Chebyshev theorem, because it applies to all distributions, bell curves as well as not bell curves, this is actually really powerful. And people use this, for example, in stock market prediction all the time, is that they're trying to find the percentage of all stock prices that are within a certain price range, for example. And you can easily use this by knowing just the mean and standard deviation.
So how do we get a percentage that's only 1 standard deviation away? If it's just gonna give us 0, check.
Yeah, so it turns out that usually in practice, we're concerned with the number of standard deviations that is greater than 1.
So are we ever gonna be asked for it if it's just 1?
No,
Okay.
no. So we just went over it just so you could see that if you had used 1, then it would be an answer that was very informative. But in practice, we usually care about standard deviations that are greater than 1. And just so you can see that the greater the number of standard deviations, the higher this percentage ends up being. Okay. And so the point of saying all this is that if you have a data point that is a large number of standard deviations away from your mean, then that means it's an extreme value that is capturing more percentage of the data. So for example, if these are the test scores, the mean is 60 and the standard deviation is 5. Let's say that you get a score that is an 80. Well, in the conventional grading scale, that's considered a B. But here, is this considered, do you think this would be considered a good grade? Would this be extreme enough to be deserving of an A? So how many standard deviations is this grade removed from the 60?
4.
Yeah, it's 4 standard deviations away from the 60. So if it were a bell curve, then it would be all the way over here, and all the values within the mean would constitute what percentage of the population? If it were 4 standard deviations away. Yeah, it would be 99.99%. So that means that your score, which is 4 standard deviations away, is in the upper 99.99% of all the test scores, which means that there's only 0.01% of test scores that's either greater than your value or less than the other extreme value over on the other side. So the point is that by looking at a certain data point and looking at the number of standard deviations, if that is away from the mean, you can tell how extreme that value is. Okay, any questions?